get integer overflow, simply use a large constant instead. As we will see, the main idea behind the Floyd-Warshall algorithm builds off the notion that you want to compute all intermediate routes between two nodes to find the optimal path. Suppose our adjacency matrix tells us the distance from a node A to a node B is 11. Now, suppose there exists a third node C. If the distance from A to C and then C to B is less than the distance from A to B, then it is better to go through node C. Again, the goal is to consider all possible intermediate paths between triplets of nodes. This means we can have something like this, where the optimal path from A to B is first going to C, then going from C to B, but in the process we actually route through another node, which I labeled with a question mark because we've already computed the optimal path from C to B, and I know that it involves an intermediate node. Similarly, we can get longer paths with more intermediate nodes between A and C and B with a smaller cost. We are also not just limited to one intermediate node in between A and C and B. We can have several, like in the graph below. Now the question comes of how do we actually compute all intermediate paths? The answer is we will use dynamic programming to cache previous optimal solutions. Let dp be a three-dimensional matrix of size n by n by n, which acts as our memo table. We're going to say that the cell dp at kij in our table gives us the shortest path from node I to node j, routing through nodes 0 through k. What we'll do is start by computing k equals 0, then k equals 1, then k equals 2, and so on. This gradually builds up the optimal solution routing through 0, then all optimal solutions routing through 0 and 1, then all optimal solutions routing through 0, 1, and 2, and etc. Up until we covered all nodes, at which point we have solved the all pairs shortest path problem. Let's talk a bit more about how to populate the dp table. In the beginning, the optimal solution from I to j is simply the distance given to us in the adjacency matrix. So when k equals 0, dp of kij is equal to mij, the value of the edge from I to j. Otherwise, in general, dp kij can be summed up with the following recurrence relation. I'm going to break it down so that we can understand all its components, because this may look scary to some people. The left-hand side of the recurrence simply says, reuse the best distance so far from I to j, routing through nodes 0 to k-1. It's important to note that the solution using nodes 0 to k-1 is a partial solution. It is not the whole picture. This is part of the dynamic programming aspect of the Floyd-Warshall algorithm. The right-hand side of the recurrence finds the best distance from I to j, but routing through node k, reusing the best solutions from 0 to k-1. If we analyze the right side of the min function, in English it basically says go from I to k, then go from k to j. Visually, this is what it looks like. You start at I, route through some nodes, get to k, and then from k, route back to j. Currently, our algorithm uses big O of v cubed memory, since our memo table dp has one dimension for each of k, I, and j. This isn't particularly great. Notice that we will be looping over k starting from 0, then 1, then 2, and so forth. The important thing to note here is that previous results build off the last, since we need the state of k-1 to compute state k. That being said, it is possible to compute the solution for k in place, saving us a dimension of memory and reducing the space complexity to big O of v squared. Now we have a new recurrence relation which no longer involves the k dimension. This has been replaced by the fact that we're computing the k+1th solution in place inside our matrix. Okay, that's all the theory we need for now. Let's get our hands dirty and look at some pseudocode. Below is the function that actually solves the Floyd-Warshall algorithm, or rather executes the Floyd-Warshall algorithm. But before we get into that, let's look at some of the variables I have defined in the global or class scope, which I will be using throughout these functions. The first variable is the number of nodes in our graph. Then is the 2D memo table that will contain our all-pair shortest path solution. Last is the next 2D table that we will use to reconstruct our shortest paths. Now moving on to the Floyd-Warshall function, you see that it takes one parameter. This is the 2D adjacency matrix representing our graph. The first thing I do in the method is call the setup function. So let's take a look at that real quick. So here we are inside the setup function. The first thing I do is I allocate memory for our tables. The DP matrix should have the same type as the input adjacency matrix. What I mean by this is if your edges in your input matrix are represented as real numbers, then your DP matrix should also hold real numbers. The next matrix will contain indexes of nodes to reconstruct the shortest paths found from running the Floyd-Warshall algorithm. It is important that initially this matrix be populated with null values. Inside the for loops, all I do is copy the input matrix into the DP matrix. Think of this as the base case, or rather the k=0 case. For the next matrix, if the distance from I to j is not positive infinity, then the next node you want to go to from node I is node j by default. Now we're back inside the Floyd-Warshall function. In here, after the setup, loop over k on the exterior loop. It's important that k is on the exterior loop since we want to gradually build up the best solutions for k=0, then k=1, then k=2, and so on. Followed by this, loop over all pairs of nodes I and j. Inside the main body actually tests for our condition to improve the shortest path from I to j going through k and update the value at dp ij if there's a better route through k. Also inside here, update the next array at ij to point to the next index at next ik. The last thing I want to do is to detect and propagate negative cycles. This is an optional step if you know that negative cycles will not manifest themselves within your graph, although I still recommend you keep this function around. But before we get too far, I want to discuss negative cycles and what they entail because it isn't entirely obvious. So consider the following graph. There are basically two types of nodes to consider here. Nodes directly involved in negative cycles, and nodes unaffected by negative cycles. This red node is the cause of a negative cycle because it can endlessly loop on itself and obtain smaller and smaller costs, while these blue nodes are not directly in a negative cycle. This, however, doesn't mean they're not necessarily safe from negative cycles, as we will see. Negative cycles can also manifest themselves as groups of nodes working together, like the following. So an important thing to ask ourselves is, does the optimal path from node I to node j go through a red node? If so, the path is affected by the negative cycle and is compromised. For example, the shortest path from 0 to 5 is negative infinity, because I can go from 0 to node 2 and indefinitely loop in the negative cycle consisting of nodes 1, 2, and 3 obtaining better and better costs before eventually going to 5. This is a consequence of traversing a red node on the way to 5. Some shortest paths, however, avoid red nodes altogether. Consider the shortest path from 4 to 6. This doesn't involve any red nodes, so we can safely conclude that the shortest path from 4 to 6 is indeed 2. So to identify whether or not the optimal path from I to j is affected by a negative cycle, rerun the Floyd-Warshall algorithm a second time. If the best distance is better than the already known best distance stored in our table dp, then set the value in the matrix from I to j to be negative infinity. Also mark the index at ij in the next matrix with a -1 to indicate that the path is affected by a negative cycle. We will use this shortly. Back in the Floyd-Warshall function, all we need to do is return the matrix dp, which contains the shortest distance from any node to any other node. This is the solution to the all pairs shortest path problem. The last thing I want to cover is how to reconstruct the shortest path between any two pairs of nodes. This method returns the shortest path between the start and end nodes specified, or null if there is a negative cycle. First, check the distance between the start and end nodes is positive infinity. If so, then return an empty path. Then, to reconstruct the path, I create a variable called @ to track the current node, and then I loop through the next array, adding the current node to the path as I go. During this process, I check if the current node has the value -1. If it does, then this means that the optimal path encountered a red node and is trapped in a negative cycle, so return null. Notice that in reality, this method has 3 key return values: an empty path, which means that the start and end nodes are not connected, a null value meaning a negative cycle was encountered, and lastly, a non-empty path of node indices to mean an actual shortest path was found. Today we're going to be looking at some source code for the Floyd-Warshall all pairs shortest path algorithm. Here we are in the source code for the Floyd-Warshall algorithm. So let's get started. Let's start by looking at an example of how to use this Floyd-Warshall solver class to actually find all pairs shortest path. So here in the main method, the first thing I do is I actually initialize a graph with n nodes, where n is set to 7, and I create our adjacency matrix by calling the createGraph method. And if we look at up here, this is the createGraph method, and all it does is it initializes a matrix of size n by n. It fills the matrix with the special constant positive infinity, and it also sets the diagonal to have all 0 nodes by default, because I assume that this is the behavior you want. If it's not, then that's not an issue, because you can just override it when you add some edge values to your adjacency matrix. All right, so we created a matrix, we added some edge weights, and then what you'll want to do is create an instance of the solver, give it our adjacency matrix, and then call the get all pair shortest path matrix function, which will return the all pair shortest path matrix as a matrix called dist for distance. And then here all I do is I loop over all pairs of nodes I and j, and I print what the shortest path from node I to j is. Here's a sample output of what that looks like. So there can be roughly 3 different kinds of outcomes. We get a concrete shortest path. There does not exist a path between the 2 nodes, that'd be infinity, and we encounter a negative cycle, so that is negative infinity. Similarly, if we want to reconstruct the paths, this is how we're going to do it. Don't be scared by any of this, it's just text being printed on the screen. So here I want to reconstruct the shortest path between all pairs of nodes. So I loop through all pairs of nodes I and j, and then on the solver, again, I call reconstruct shortest path from I to j, and that returns a list of nodes. And here I just print 3 different options depending on when I get back. If the path is null, then there does not exist, or rather, sorry, there exists an infinite number of solutions. If the path has 0 length, there is no solution. And otherwise, I just do a pretty formatting of the output. And this is what that would look like. So it just prints what the path would be between all pairs of nodes. So for instance, the shortest path from node 0 to node 2 in our graph goes through nodes 0, 1, and 2. And it just prints all this information for all nodes in our graph, which is really useful. Okay, so what is this Floyd-Warshall solver actually doing? And that's what we're going to look at right now. So inside that class, we have 4 instance variables. N, the number of nodes in our adjacency matrix, a Boolean value called solved, which just tracks whether we've solved the all pairs shortest path problem or not, our DP matrix, and a next matrix, which is used to reconstruct the paths. And there's also this constant, which I just initialized to -1, so we can identify when we've reached negative cycles. Okay, so looking at the constructor, again, you just pass in the input adjacency matrix, and then I do some initialization. So simply allocate memory for our matrices that we're going to need, and then populate the DP matrix with whatever is given to us for our input. And also make sure to initialize the next matrix to contain j as the next value going from I to j. And that's all you need to do for the setup, nothing too complicated. Let's look at some of the methods that are provided in this class. The first one is get all pairs shortest path matrix, which is the first method we called. And what that does is it looks if we've solved the all pairs shortest path problem already, and if not, it calls the solver. The reason I do this is so that if we want to get the all pairs shortest path matrix multiple times, that we don't run the solve method several times. So the solve method is what actually solves, or rather executes, the Floyd-Warshall algorithm. And here's what we're going to do to compute all pairs of shortest paths. First, we iterate through k on the exterior loop. And then we loop through all pairs of nodes, and then we check for our condition. So if the path going from I to k and then k back to j is less than the path from I to j, then update the value of I to j to route through that node k. And while doing this, also